This is the second part of the 12th lesson in heat transfer. In the 12th lesson, we are continuing our discussion of steady-state multidimensional conduction heat transfer, analyzed using the finite volume method. In this part of the lesson, we will be looking at solving the finite volume method equations in a two-dimensional case. In the first part of the lesson, we looked at a simpler case of a one-dimensional heat transfer problem in order to see that the finite volume equations represent a coupled set of linear algebraic equations that can be most easily solved using matrix inversion methods. By the end of this lesson, you should be able to order the nodes in a two-dimensional mesh in order to assemble the coefficient matrix. You should also be able to use matrix inversion methods to solve the equations simultaneously in the MATLAB environment for a two-dimensional heat transfer case. On with the lesson. As a reminder, the finite volume method consists of 3 steps. The first step is to create a numerical mesh. This involves defining the nodes, the faces of the volumes. The next step is to identify or derive the governing equations for each node or volume in the numerical mesh. Finally, we solve those equations simultaneously. Solving the equations has been the focus of the 12th lesson. In the previous lesson, we saw that the coefficient matrix is non-zero on and near the main diagonal in one-dimensional problems. We looked at a simple one-dimensional case. The example that we analyzed is repeated here for review. We had a long square rod that was 1 meter on its side and had a length of 1.1 meter. The rod had a known temperature at one end and convection heat transfer on the other. When we looked at the governing equations for each of the volumes, we saw that they could be represented in a matrix form as follows. Here we have the constants matrix, the coefficient matrix, and the unknown temperatures matrix. Notice that the non-zero elements of the coefficient matrix reside on or near the main diagonal in this one-dimensional heat transfer case. We have mostly -2's on the main diagonal, 1's on the lower diagonal, and mostly 1's on the upper diagonal, except for the first row, which corresponds to the known temperature T1 boundary condition. In a two-dimensional problem, non-zero elements will also reside away from the main diagonal. To see this, we will look at a simple two-dimensional heat transfer case of heat transfer on a square. I will read the problem statement now. A solid square with a side length of 1 meter is held at 100 degrees C on its left side and 200 degrees C on its bottom side. Left side and bottom side. The right and top sides of the square are exposed to a flowing fluid. The temperature of the fluid is 0 degrees C, and the flow gives rise to convection heat transfer characterized by a convection coefficient of 4 watt per meter squared Kelvin. We'd like to estimate the temperatures in the square using finite volume method with a grid spacing of 0.25 meters. The first step is to define a numerical mesh. We were tasked with using the finite volume method using a grid spacing of 0.25 meters. When we use a grid spacing of 0.25 meters, we end up with nodes that are 5 in one direction and 5 in the other, because there are 0.25, 0.25, 0.25, 0.25 meters between each node, and the side length of the square was 1 meters. We thus have 25 nodes in our numerical mesh. It is 5 by 5. We need a way of keeping track of the nodes. There are 2 options. One is to order the nodes increasing first in X and then in Y, as is done here. We start at the top left and assign a number to each node, 1, 2, 3, 4, 5, increasing the number first in the X direction and then moving sequentially row by row. 6, 7, 8, 9, 10, and so forth. The other option would be to order the nodes increasing first in y and then in x. 1, 2, 3, 4, 5 down the rows, and then over in the columns. 6, 7, 8, 9, 10, 11, 12, and so forth. While either option is perfectly valid, in this lesson we will choose option A. Now that we have created the mesh and ordered the nodes sequentially first in x and then in y, we now need to identify the governing finite volume method equations. There are 5 types of equations in this particular mesh. First, we have interior nodes. We have 9 interior nodes. The governing equation is most easily obtained from case 1 in table 4.2. The 9 interior nodes are nodes 7, 8, 9, 12, 13, 14, and 17, 18, and 19. I've highlighted node 13 here as representative of this particular case. From table 4.2, the governing equation is provided. We can map this to our node counting convention. Anytime there is an m-1, that means we are moving a column to the left. And that becomes, if k is the 13th node, the 12th node, it is the k-1 node. m+1 is the node to the right. In this case, it would be, if k represents the 13th node, the 14th, the k+1. We also have an mn+1. This denotes a node above the node number 13. In this case, we subtract 5, which is the number of nodes in the x or the y direction. And we have kn-1 is 8. We also are adding tmn-1. That represents the node below node 13, which in this case is 13 plus 5, 18. So we denote that with a k plus ni. And then we subtract 4 times the temperature of the node of interest, T sub k. This equation applies for nodes 7, 8, 9, 12, 13, 14, 17, 18, and 19. The other type of finite volume equation are for the nodes at the right surface with convection. This is case number 3 from table 4.2. There are 3 nodes with this case, 10, 15, and 20. From the table, the governing equation is given as follows. We need to link the provided equation to our particular node counting convention. The same approach applies. m-1 corresponds to a node to the left. If we are looking at node 15, that would mean node 14. And if k represents the 15th node, then the m-1 n node is k-1. We also have mn+1. This represents a node below node 15. In this case, that is the 15 plus 5, the 20th node, the k plus 5, or the k plus ni. And we have mn-1 that represents the node above. In this case, that is the node 10, where the 15 minus 5 is 10, k minus ni. Linking these then, we replace tm-1n with tk-1, tmn+1 with tk minus ni, that's the 10th node, and we replace mn-1 with k plus ni, that's the 20th node. tmn becomes node tk. K can be 10, 15, or 20 in this particular condition. The third type of case that we have are nodes at the top surface with convection. This is case number 3 from table 4.2. Nodes 2, 3, and 4 fall into this particular case. We can also use case 3 from table 4.2. We just have to translate the information. Here we have now the tmn-1, which is the case for conduction from the node on the interior. We have plus 0.5 times the neighboring nodes, where there is conduction through half the area of a volume, face of the volume. So we have Tmn minus 1 here in this position rather than Tm minus 1n. And we have Tm plus 1n and Tm minus 1n rather than Tmn plus 1 and Tmn minus 1 because of the different face on which this boundary node is located. We apply the same convention to replace the mn terms with the appropriate translation into R counting convection using k as a counter. The mn minus 1 is replaced with k plus ni. Looking at node 3, if node 3 represents k is equal to 3, then we have node 8 below, which is the k plus ni, 3 plus 5 condition. For m plus 1 and m minus 1, we have the node to the right and to the left respectively. K minus 1 to the left, k plus 1 to the right. I have moved the constant to the left-hand side. The fourth case is the node at the external corner with convection on two sides. This is case number 4 from table 4.2. The equation provided in table 4.2 is as follows. We need only now translate this into our particular node counting convection. The mn minus 1 represents the node below mn. That is the k plus ni node. K represents 5, plus 5 is 10, and ni equal 5. The m minus 1n node is the node to the left of the corner node. In this case, it is 5 minus 1, k minus 1 node. Finally, we have nodes that are at known temperatures. This represents nodes 1, 6, 11, 16, 21, 22, 23, 24, and 25. The equation for nodes at known temperature are the simplest. We simply set the nodal temperature to the known temperature T star. Mn is replaced with the kth node, and we either put in Tb for nodes that are at the bottom surface, or TL for nodes that are at the left surface. Before we begin to assemble the constants and coefficient matrix, we note that the term h delta x over k in this particular problem is equal to 1, because h is 4 watt per square meter Kelvin, and the nodal spacing is 0.25 meters, and the thermal conductivity is 1 watt per meter Kelvin. Because T infinity is set equal to 0, when we multiply that by 0, this term becomes 0. We are now in a position to solve the finite volume method equations. The first step in solving these equations in the 2D case is to assemble the constants matrix. This is similar to what was done in the one-dimensional case, but here we have more equations to keep track of. I have repeated the numerical mesh, and what I have done in the table is I have listed the constants for each node. There are 25 nodes and 25 equations. There are thus 25 left-hand sides. Let's look at each particular case of the equation that we encountered. Interior nodes had a left-hand side equal to 0. These nodes are 7, 8, 9, 12, 13, 14, 17, 18, and 19. The left-hand side was equal to 0 in these cases. Case 2 corresponded to nodes that had convection boundary conditions on the right-hand side. This corresponds to nodes 10, 15, and 20. Case 3 were convection boundary conditions on the top side. This corresponds to nodes 2, 3, and 4. Because we have chosen to order our nodes increasing in x first and then increasing in y, these three nodal constants show up next to each other rather than spaced out in the constants vector. Finally, our fourth case corresponded to the node on the corner, which had convection on 2 of its faces. It shows up in position number 5. It is the 5th node. All of the nodes at known temperature have the known temperature placed in the constants matrix. We have known temperatures at nodes 1, 6, 11, 16, 21, 22, 23, 24, and 25. You can see those temperatures denoted here: 1, 6, 11, 16, 21 through 25. You have chosen to set the 21st node equal to 200. One could also solve the problem with the 21st node set equal to 100. Now that we have assembled the constants matrix, we must also assemble the coefficient matrix. I have done that separately from this video. The result is shown here. Because we have 25 equations, the coefficient matrix is a 25 by 25 table. 25 rows corresponding to the 25 nodal temperatures and equations. Let's go through and look at each of the 5 cases of equations that we encountered when we are analyzing our mesh. We should see those coefficients show up here in our matrix. First, we consider the interior nodes. The interior nodes had 4 neighbor temperatures and the node temperature, and there was a -4 for the node temperature. Let's go quickly review that. Here is that equation. So we have 1s for the neighboring temperatures and a -4 for the node of interest. You can see the 1s for the 4 neighboring temperatures and the -4 for the node of interest in each of these rows of the coefficient matrix. In the second case, we had convection boundary conditions on the right side of the square. Here we should see 0.5s for 2 neighboring nodes, a 1 in one neighboring node, and a -3, because this h delta x over k is equal to 1. We see 2 0.5s, a 1, and a -3 on the main diagonal, because that is the node of interest. In the third case, we had convection boundary conditions on the top side. We should see 0.5 on the diagonals next to the main diagonal, and a 1 on the off diagonal. That is what we see. -3s on the main diagonal. The fourth case corresponded to the boundary condition on the corner. We should see 0.5 and -2 on the main diagonal. -2 on the main diagonal, 0.5 on the near neighbor, and 0.5 on the off diagonal. Finally, the known temperature boundary conditions simply has a 1 on the diagonal position in order to set these temperatures to the known boundary temperature. Hopefully you now see how the coefficient matrix simply provides a representation of the governing equation. Notice that in this two-dimensional coefficient matrix, we still have mostly non-zeros on the main diagonal. But in the two-dimensional case, there are also non-zero components away from the main diagonal. That is the main difference between a one-dimensional finite volume problem and a two-dimensional finite volume problem. Now we invert the coefficient matrix to calculate the temperatures. I apply T is equal to A\C in MATLAB. The result is given as follows. We have 100 set for nodes 1, 6, 11, and 16, 200 set for nodes 21, 22, 23, 24, and 25, and we have calculated the unknown temperatures on the interior of the square at the remaining 16 nodes. The top right corner is coolest. This is the corner farthest away from the heated sides and closest to the cold fluid at 0 degrees C. This is a relatively coarse mesh. We can greatly increase the approximation of the temperature field by using a finer mesh. Here is an example of a finer mesh using volumes that are 1 centimeter on a side. So we have node spacing here of 1 centimeter. The bottom surface of the square is at 200 degrees C. The left-hand side is at 100 degrees C, and heat transfers from these hot sides through the square to the sides with convection heat transfer. This is the end of the 12th lesson, which is focused on solving the finite volume method governing equations. Future lessons, we will look at how we interpret these solutions in order to calculate rates of heat transfer, and also to verify whether the solutions are correct or not.